Hello and welcome to the lecture on 7.3. Today we're going to talk about the double angle identities. We're also going to talk about the half angle identities and power reducing formulas, but they mostly all come from the double angle identities, which are more important. As a note, the most important identity is cosine of theta plus phi is equal to cosine of theta, cosine of phi, minus sine theta sine phi. I say the most important, it's more that it's the most powerful identity that we have, because most of the other identities will come from the double angle cosine identity, and we derive the double angle cosine from the sum of angles cosine identity. We also derive the double angle for sine in the same way, so I'm also going to say recall that sine of theta plus phi is equal to sine theta cosine phi plus sine phi cosine theta. Now let's go ahead and derive the double angle cosine identity. Specifically, what it looks like is this, cosine of 2 theta. What does this give us? Well, it's really easy to see if you just let theta and phi be the same angle. If we say that phi is equal to theta, then we replace phi with theta, and we end up with cosine of theta plus theta, which is cosine of 2 theta, the double angle identity. But replacing phi with theta on the left means that we have to replace phi with theta on the right as well. So we end up with cosine theta times cosine theta, which is going to be cosine squared theta, minus sine theta, which is sine squared theta. So this is the first double angle identity for cosine. Now cosine has 3 different forms. If we recall, sine squared x plus cosine squared x is equal to 1, then we can look at it in different forms and say that sine squared x is equal to 1 minus cosine squared x, and cosine squared x is equal to 1 minus sine squared x. These are the different forms of the Pythagorean identity. Now, if we replace cosine squared with 1 minus sine squared, we end up with the second formula, which would say, instead of cosine squared, we have 1 minus sine squared, so it would be 1 minus sine squared minus another sine squared. So we end up with 1 minus 2 sine squared theta. This is the second double angle cosine identity. And the third would be exactly the same thing, except we replace sine squared with 1 minus cosine instead. So we would end up with 2 cosine squared theta minus 1. These 3 are the double angle cosine identities. Now if we do the same thing with sine, so we say, again, phi is equal to theta, we do sine of theta plus theta, we end up with sine 2 theta. And again, if we replace phi with theta on the left, we have to replace phi with theta on the right, which means we would have sine theta cosine theta plus sine theta cosine theta, which gives us 2 sine theta cosine theta. And this is the double angle sine identity. Now tangent, you can find exactly the same way by just changing your phi into a theta, or you can just do sine over cosine as well. It doesn't really matter. But all that is to say that tangent of 2 theta is exactly 2 tangent of theta divided by 1 minus tangent squared theta. So here are my double angle identities. Again, they come from the sum of angles identities, just by replacing phi with theta. Now, how do we use this? It's very similar to pretty much how we use the sum of angles identity. So let's show that cosine of 60 degrees is equal to 1/2. And I know we already know this, but let's use the double angle identity to show this. Suppose we didn't know cosine of 60 degrees, but we knew what cosine of 30 degrees was. So we know cosine of 30 degrees is equal to root 3 over 2. And we're pretending not to know that cosine of 60 is equal to 1/2. So what we would say then is cosine of 60 degrees is equal to cosine of 2 times 30 degrees. And we can reduce this to cosine squared 30 degrees minus sine squared 30 degrees. Or we could use one of the other ones. If we only knew cosine of 30 degrees, we could just use this one. If we only knew sine of 30 degrees, we could use this one. It doesn't really matter. I'm just going to go with the first one. Now, cosine of 30 degrees is root 3 over 2, and then we square that. So we have root 3 over 2 squared. And sine of 30 degrees, of course, is 1/2. And we square that. So we end up with 3/4 here minus 1/4, which would be 2/4, which of course is equal to 1/2. Now I want to note here that when we have an angle that we don't know, it's twice as much as an angle that we do know. You want to write this step where you have 2 times an angle that we know. This helps materialize what you're actually doing, because a lot of times students will get confused by the angles here and here. You'll get confused between them, and you'll try to multiply 60 by 2 on accident. You don't want to multiply 60 by 2. You want to rewrite 60 as 2 times some other angle, which is what I did here. So when you're doing these problems in the beginning, you want to write out this step. It will be helpful later on. Do another example, a little bit more of an example. If sine of x is equal to 3/5, where x is in quadrant 2, find sine of 2x and cosine of 2x. So if I know sine of x is equal to 3/5, then I can draw a triangle where I have an angle x. Now I draw my triangle in quadrant 2. This point here would be the origin of a circle, and we would have the angle like this. This is angle x. And we do have our triangle, and it is sine of x, so we know that the opposite over the hypotenuse is 3/5. Now be careful, because we're in quadrant 2, our x is negative. Our x value, I should say. It's kind of confusing that we have an angle x and then an x value here. But I'm referring to this x value. Actually, let's change this so that we have thetas instead, so that we're not so confused. So we have sine theta is equal to 3/5, which means that this has to be a theta as well. Now I'm looking for my x value, which is to the left, which means it's negative. Now if we use the Pythagorean theorem, we would end up with -4. It could be +4 or -4, but of course we're to the left of the y-axis, which means we have a negative x value. Then all we need to do is find sine of 2 theta. Now my problem is I only know what theta is. I only know sine of theta, and I can figure out cosine of theta. So this is twice this angle, which would mean it would be down here somewhere. Now I don't know what sine is down there. I have no idea. But we can rewrite sine in terms of sine and cosine of a single theta instead of 2 theta. This, of course, is 2 sine of theta, cosine of theta. So we end up with something like this. Now notice that sine and cosine are now written in terms of a single theta. So we have sine of a single theta, cosine of a single theta. We have our theta here. So I can figure this out. Sine of theta will be 3/5. Cosine of theta will be -4/5, adjacent over hypotenuse. This would be 2 times 3/5, which was given in the problem, and then -4/5 here, because we just do the adjacent over hypotenuse of this triangle here. So 2 times 3 is 6, 6 times 4 is 24. We end up with -24 over 25. Now cosine of 2 theta, we can use any of the forms that we want. I'm going to use a different form than the one that I used last time. I'm going to use this one, because I already know what sine 2 theta is, so I can just figure this one out pretty easily. So we do 1 minus 2 sine squared theta. They'll all give you the exact same value. Doesn't actually matter which one you use. I just want practice using them all. So we do 1 minus 2 times. Now, sine theta is 3/5, but we are squaring sine, so I have to square this. We end up with 1 minus 2 times 9 over 25. This would be 18 over 25. And 1 minus 18 over 25 is 7 over 25. And then we're done. That's all we need to do. Go ahead and try one. If tangent of theta is equal to 5/12, where theta is in quadrant 3, find sine of 2 theta and cosine of 2 theta. Should be able to just follow the same steps. Make sure that you draw your triangle in quadrant 3 though. Do another example. This one's more of a theoretical problem, but still fun nonetheless, and it gives us practice. Write sine of 3x in terms of sine of x. Now this one's a bit tricky. You have to be careful here. We don't have a triple angle identity yet. I mean, we're about to derive one, but we don't have one yet. So how do I just put this in terms of sine of x? I can't pull the 3 out. That doesn't make sense because we have identities for sine 2 theta. Why would we be able to pull the 3 out if we can't even pull the 2 out? So what we have these identities for is to deal with the double angle and multiple angles. So what I'm going to do instead is I'm going to couple the double angle identity with the sum of angles identity. So we do sine of 2x plus x, like this. Now I have a sum of angles, and I know a formula for that, and one of my angles will be a double angle, and I can just use the double angle identity. So this becomes sine of 2x, cosine of the second angle x, plus sine of the second angle x, cosine of the first angle 2x. All right, pretty nice so far. Now I just need to rewrite sine of 2x in terms of a single x. Similarly, I need cosine of 2x to be in terms of a single x instead of a double angle. So sine of 2x is, of course, 2 sine x cosine x. This cosine x carries down. This is my sine 2x. And then we have sine x here. Cosine of 2x, I'm going to write using the second identity, which is 1 minus 2 sine squared x, because we're trying to get it into terms of x already. So if we use that one, we've already done that. We do 1 minus 2 sine squared x. So I have sine x is here, sine x is here. I have two cosines. This is cosine squared, and then I have a sine x. So we're well on our way here. 2 sine of x, cosine squared, plus sine x. Distributing this, we get sine x minus 2 sine cubed x. Okay, now how do I deal with this? Well, remember that we also have the Pythagorean identity. So recall 1 minus sine squared theta is equal to cosine squared theta. This is a form of the Pythagorean identity. So cosine squared can be rewritten as 1 minus sine squared. So I'm going to replace my cosine squared with 1 minus sine squared. So we get 2 sine x times 1 minus sine squared x plus sine x minus 2 sine cubed x, just like that. Distribute this 2 sine x through, and we get 2 sine x minus 2 sine cubed x plus sine x minus 2 sine cubed x. Now we just combine like terms and we are done. So we have 2 sine x plus another sine x. This would be 3 sine x. And then we have negative 2 sine cubed x minus 2 more sine cubed x. This would be minus 4 sine cubed x. And just like that, we've derived an identity for the triple angle. Now, this is not anything special, but it's still nice to have sometimes. Try a problem. Use the triple angle identity in the previous example to find sine 3 theta if cosine theta is equal to 4/5, where theta is in quadrant 4. This might be a little bit tricky, but I think you should be able to do this one on your own without too much help. Make sure you draw a triangle for this, and that's all I need to say. I think you should be able to get it from there. Next topic I want to talk about is the power-reducing formulas. I've said before that the sum of angles for cosine is one of the more powerful identities that we have. And that's because it gives us the double angle identity. If you recall, cosine of 2x is equal to 2 cosine squared x minus 1, and cosine of 2x is equal to 1 minus 2 sine squared x. Here, notice that we have a squared term for cosine, but we can reduce that down to a non-squared term. And this is very helpful to us, especially moving forward into calculus. Similarly, we can reduce a sine squared into a cosine with a single power. Now, granted that our angle is now going to be twice the angle that we had prior, but we can reduce the power, which is really helpful. So what if we solved for cosine squared here? That means adding 1 and dividing by 2. So cosine squared x would equal 1 plus cosine 2x divided by 2. We can also solve for sine squared here. And that will be done by adding sine squared over, subtracting cosine 2x, and then dividing by 2. So we end up with sine squared x is equal to 1 minus cosine 2x divided by 2. Now, we have it in the form where we're taking a power that is 2 and we're reducing it to a power that is 1. Notice that the angle does double, but we can deal with that. That's fine. It's important to be able to reduce a trig function to be a power of 1. Let's go ahead and formalize this. Power reducing identities. Cosine squared x is equal to 1 plus cosine 2x divided by 2. Sine squared x is equal to 1 minus cosine 2x, also divided by 2. And tangent squared x, now here we can just take sine squared divided by cosine squared, and we end up with 1 minus cosine 2x divided by 1 plus cosine 2x. Keep these in your head when we move to the half angle identities in a bit here, because these are going to derive the half angle identities. Also keep in mind that our angle doubles. This is part of the formula that our angle will double. But let's say that we had something like this, where we had cosine squared of 4x. Okay, so notice that my angle is changed. It's 4x here. I want to reduce this to be a power of 1 for cosine. Now, because my angle is 4x, I need to double this angle in my formula. So doubling 4x will become 8x, but nothing else changes. Everything else is fixed in the formula. 1 plus cosine. This will be 2 times our angle 4x divided by 2, which of course is 1 plus cosine of 8x divided by 2. Whenever you apply the double angle identity, you always double this angle. which is why we have a 2 times 4x here, or just 8x. Let's do another example. Now, this example gets a little tricky. Right, sine 4x in terms of the first power of cosine. So what we're trying to do here is we're trying to reduce the power of sine to the fourth to be just a single power. Now we can't do that with sine, obviously, because sine squared gives us a cosine to the power 1. So we're always going to have a cosine in our answer here instead of a sine. Now there's a couple of ways to do this, but I'm going to go with the way that I think most students will do. So we have sine to the fourth of x will equal sine squared x times sine squared x. Now I can reduce the power of this sine squared and this sine squared. And we get 1 minus cosine 2x divided by 2 times 1 minus cosine 2x divided by 2. Now, are we done? The answer is no, unfortunately. Because we have this multiplication here, where we're multiplying these two numerators, we're going to get a term that is cosine 2x times cosine 2x, which is cosine squared of 2x. But we want first powers of cosine only. So we keep going here, and we FOIL at the top. I'm going to write my 1/4 off to the left. We have a 2 times 2 in the denominator. That makes a 1/4. And then I'm going to write my, my terms here. I just FOIL out the top. So this will be 1 times 1, which is 1, minus 1 times negative cosine 2x, and negative cosine 2x times 1 will give us 2 negative cosine 2x's, and then plus our cosine 2x times cosine 2x, which is cosine squared 2x. Okay, so again, notice that we have a cosine squared. We need to get rid of this. We need to make it a first power of cosine. So how do we do that? Well, we go back to our identity. Now we have a cosine squared of some angle. Think of x as just some angle. It doesn't matter what it looks like. It's an angle. Anything inside this parentheses is an angle. So we have cosine squared of some angle is going to be 1 plus cosine of twice that angle divided by 2. So inside our parentheses, we have a 2x. So this will become 1/4, 1 minus 2 cosine 2x, plus, now we have to apply the power reducing formula to this cosine squared. And we get 1 plus cosine 2 times 2x, because 2x is our angle. So we have to double it. We get 4x here, divided by 2. And then a little bit of simplification. I can pull this 1/2 out. I end up with 1/8. Now when I pull that 1/2 out, this becomes a 2 and this becomes a 4. I have 2 minus 4 cosine 2x plus 1 plus cosine 4x. You can combine this 1 and 2 and you get 3, and you cannot combine this cosine 4x with the cosine 2x. These two things are different. We have a different angle. So think of it like this, if you are thinking that you might be able to combine them. Suppose that this is our angle 2x. So this angle here would be this angle. Now this cosine would have an angle that's closer to here. This would be about 4x. Now they have very different x values. Notice that our x value here is different than our x value here. That would be the cosine of that angle. So because they're two different angles, I can't actually combine them when I'm adding. So our final result is 1/8, 3 minus 4 cosine 2x plus cosine 4x. Go ahead and try one. Write sine squared x cosine squared x in terms of the first power of cosine. Now, you're gonna follow a similar pattern, but it'll multiply out a little bit easier. So this problem is a little bit easier than the previous problem. Next thing I want to talk about is the half angle identities. Recall what we just went over, namely the power reducing formulas. Sine squared x is equal to 1 minus cosine 2x divided by 2, and cosine squared x is equal to 1 plus cosine 2x divided by 2. All right. Now, when we do a half angle, it's the exact same formula. Exactly the same. We're only changing it very slightly. It's exactly the same as the power reducing formula. So now I'm going to replace my x from this line to this line with x is equal to theta divided by 2. That's all I'm doing right now. So we substitute theta divided by 2 for x, and we have sine squared theta over 2 is equal to 1 minus cosine. X is theta over 2, remember? So we would have 2 times theta over 2. So we're just left with cosine of theta. And then cosine squared theta over 2 is equal to 1 plus cosine. Again, we're replacing x with theta over 2. So we would have 2 times theta over 2. So we would just get theta here divided by 2. Now I want you to notice this angle, again, is twice this angle. It's 2 times this angle. Theta is 2 times theta over 2. It's important to note that because a lot of students get confused between the half angle and the power reducing formulas. They are the exact same formula with a minor substitution. The only other difference is that we take the square root of both sides. That's it. So I'm going to formalize this right here. After we take the square root of both sides, we get our half angle formula. So here are our half angle formulas. Sine x over 2 is equal to plus or minus the square root of 1 minus cosine x over 2. Cosine x over 2 is equal to plus or minus square root of 1 plus cosine x divided by 2. And tangent x over 2 is equal to 1 minus cosine x over sine x, or sine of x divided by 1 plus cosine x. Pretty easy to prove, not too hard, so I'm not going to worry about it. Notice tangent doesn't have a square root. It's beside the point. We deal mostly with sine and cosine. I want to note here, again, this angle is 2 times this angle because it's exactly the same formula as the one we just used, the power reducing formula, which again means that they come from the double angle identity of cosine. Again, very powerful identity. I want to note also that the sign on the square root function here, this is going to come from the angle x over 2. So if the angle, the original angle that we're looking for, x over 2, is in the first quadrant, then all of these would be positive, sine, cosine, and tangent. Now, if we were in the second quadrant for the sine function, we would still use positive. But if x over 2 is in the second quadrant for cosine, we would use the negative because cosine is negative in the second quadrant. I'll explain that when we do an example. Example, find cosine of 67.5 degrees. Now here, we're going to use the double angle identity. We can't use sum, we can't use difference. We have to use the double angle identity. Now, this one might be a little bit tricky, so let's work this one out kind of slow. First, we need to rewrite 67.5 as an angle divided by 2. So we multiply top and bottom of 67.5 by 2. So we would have, say, 67.5 degrees, multiply by 2, and divide by 2. And we get 135 degrees divided by 2. 135 degrees divided by 2 is 67.5. So I'm going to rewrite that as my input for my cosine function. Cosine of 135 degrees divided by 2. Now I've set it up in my half angle identity form. I have an angle divided by 2. So now I can rewrite this as plus or minus the square root of all of this. 1 plus cosine of x divided by 2. We have plus or minus the square root 1 plus cosine 135 degrees divided by 2. Now, our question is, do we use the positive angle or the negative angle? This is where it gets a little bit tricky. A lot of students mess this up, so be careful. If we were looking for cosine of 135 degrees, we would be in the second quadrant, which would mean we would use the negative. If we're looking for cosine of 67.5, we're in the first quadrant, so we use the positive. So which one do we use? Do we look at the 135 degrees, or do we look at the 67.5 degrees? The answer is, what are we actually looking for? So don't get lost in the numbers. Go back to the original question. We're looking for cosine of 67.5 degrees. We're looking for this angle. Where is this angle? What quadrant is this angle in? It's in quadrant 1, so we actually use the positive. So this will be positive square root 1 plus, now cosine of 135 degrees is negative root 2 over 2, and then divided by 2. Now if you don't want to simplify, I understand. I'm going to go ahead and simplify this a bit. And we have the square root of, if we find a common denominator between 1 and negative root 2 over 2, it's 2. So we end up with 2 minus root 2 divided by 2, all divided by 2. Which would then mean that we can flip the denominator and multiply. Now this is 2 over 1. So when we flip, we get a 4. And it will come out to the square root of 2 minus root 2 all over 2. So the step from here to here, there's an intermediate step that I didn't do, which would be the square root of 2 minus root 2 divided by 4. Now when you're taking the square root of a fraction, you can take the square root of the numerator and the square root of the denominator. So I took the square root of the numerator, which is this, and then the square root of the denominator, which is just 2. That's where the 2 came from for here. Right, I'm going to do another example, this time in radian measure, to show you a little bit of a difference. Find sine of 13 pi over 8. Now you might not know immediately what to do here, but we're going to start exactly the same way as we did before. We need to rewrite our angle in a form such that we have an angle divided by 2, specifically an angle that's on the unit circle. So if we rewrite this as 13 pi over 4 divided by 2, then we've accomplished that. 13 pi over 4 is not on the unit circle that you've memorized, but if we continue moving around the unit circle, we'll eventually get to 13 pi over 4. So it is still on the unit circle, it's just not on the one that you've memorized. Now when we rewrite this, we have sine of 13 pi divided by 4, all divided by 2. And this will equal, plus or minus, the square root of 1 minus cosine 13 pi over 4, all divided by 2. Now notice, now we need to figure out where 13 pi over 8 is, because this is what we're looking for. This is the angle that is the input of the function that we're looking for, sine of 13 pi over 8. So what quadrant is 13 pi over 8 in? Well, remember that quadrant 1 goes up to pi over 2. And if we rewrite pi over 2 with a common denominator of 8, we will have 4 pi over 8. Clearly, 13 pi over 8 is larger than 4 pi over 8. So we continue. This is pi. Same thing as 8 pi over 8. Again, 13 pi over 8 is larger than pi, so it might be in quadrant 3 or 4. This is 3 pi over 2, which is equal to 12 pi over 8. Now, 13 pi over 8 is a little bit larger than 12 pi over 8, so we know we're in quadrant 4, because this would end at 2 pi, which is 16 pi over 8. So we're in quadrant 4 here. So we can say that our angle 13 pi over 8 is in quadrant 4. Now, our question then becomes, is sine positive or negative in quadrant 4? Negative. We use this sign here. We'll end up with negative square root 1 minus. Now we need to figure out what cosine of 13 pi over 4 is. Safe to say that it's going to be a root 2 over 2. Now, whether it's positive or negative depends on the quadrant of 13 pi over 4. And we can just rotate around. 1 pi over 4, 2 pi over 4, 3, 4, 5, 6, 7, 8 pi over 4, 9 pi over 4, 10, 11, 12, 13 pi over 4 is in quadrant 3. So we know we're going to have a negative x value. So this is actually going to be negative. We get negative root 2 over 2, all divided by 2. So this will end up being negative square root 2 plus square root 2 all over 2. That's if we do the simplification. This is what you should get as your answer. Now I want you to try one because these are challenging and you need to practice. Try one. Find cosine 7 pi over 8. All right, let's continue. Do another example. Find cosine of x over 2 if tangent of x is equal to 4 over 3, where x is in quadrant 3. So tangent of x is positive, but tangent is positive in quadrant 1 and quadrant 3, so we know that x is in quadrant 3, so we can draw a triangle accordingly. Be something like this. This would be our angle x in quadrant 3. Now, it doesn't stop tangent from being 4/3. We just know that this is -4 and this is -3 now. Hypotenuse is 5. It's a 3, 4, 5 triangle. It just helps to write it this way so that we can see when we have positive and negative values. Now we're looking for cosine of x over 2. Now this is a bit tricky also. We know that x is in quadrant 3, but we need to know if x over 2 is in quadrant 1, 2, or 3. Let's list out our quadrant 3 bounds. What angles bound quadrant 3? Well, we know this is pi and this is 3 pi over 2. So we know that x is between pi and 3 pi over 2. X has to be within these bounds. Otherwise, it can't be in quadrant 3. So that we then need to figure out which quadrant x over 2 is in. So, because we need to figure out where x over 2 is, we divide by 2, divide by 2, and divide by 2. And we know then that pi over 2 is less than or equal to x over 2, the entire angle that we're looking for, which is less than or equal to 3 pi over 4. So what quadrant is this in? Well, if x over 2 is larger than pi over 2, we know it's larger than this vertical line because this is pi over 2, this angle here. So we know that we're in quadrant 2 because we're between pi over 2 and 3 pi over 4. X over 2 is somewhere over here, somewhere in this range. So because x is in quadrant 3, this implies x over 2 is in quadrant 2. This is tricky. A lot of students mess this up, so please try to understand. If you need to, go back through this part, this explanation. Right. Now, cosine of x over 2 is then equal to plus or minus the square root of 1 plus cosine x divided by 2 And which sign do we use? Do we use the positive or the negative? Well, x over 2 is what we're looking for, cosine of x over 2. And x over 2 is in quadrant 2, and cosine is negative in quadrant 2. So we use the negative sign. We end up with negative square root 1 plus cosine x divided by 2. Okay. Now we need to figure out what cosine of x is. We know what tangent of x is. We just need to figure out what cosine of x is. We have our x here, and we have our triangle. Cosine is negative root 3 divided by 5. So we would end up with negative square root 1 minus 3/5 all over 2. We find a common denominator between 1 and negative 3/5. That's going to be 5, so we would have 5 over 5 here. 5 minus 3 is 2. So we'd have 2/5 in the numerator. This will be equal to negative square root 2/5 divided by 2. And of course we can write 2 as 2 over 1 because it's a whole number. Flip and multiply and we end up with just 1/5. So we have negative square root 1/5. That's what cosine of x over 2 is. If tangent is equal to 4/3 and x is in quadrant 3. Do another example here. I know there's a lot of examples in this section, but there's a lot of different types of problems that we can use, especially since we have the double angle, half angle, and power reducing formulas. Evaluate. Sine of 2 times cosine inverse of x over 2. Whenever we have a formula for an angle, sine 2 theta, cosine 2 theta, it doesn't matter. We can always write that angle as the inverse trig function of something. Remember, the inverse trig functions output an angle. So we can think of cosine inverse of x over 2 as just an angle theta. And generally, I like to write it. So theta is equal to cosine inverse of x over 2. Now the reason that we need to do this is because I have sine 2 times an angle, keeping in mind that the inverse trig function is just an angle. So I can figure out a triangle for this angle theta, but I can't use that information unless I have trig functions of a single theta. Here I have 2 thetas. So we need to rewrite this as cosine of theta is equal to x over 2 so that we can draw a triangle. I'm going to assume that my angle is in quadrant 1 because it's not given. We have this. This will be angle theta, adjacent over hypotenuse, and this will be 4 minus x squared if we use the Pythagorean theorem. Now, look closely. We have a triangle with an angle theta, but if we rewrite this using cosine inverse of x over 2 equaling theta, we have sine of 2 theta. 2 theta and theta are not the same angle. In fact, 2 theta is exactly double this angle, meaning that we should rotate twice as far. But we don't have a triangle for that. So how do we figure it out? Well, we just use the double angle formula. This is equal to 2 sine theta cosine theta. Now I have my function sine 2 theta in terms of single thetas. Sine theta, cosine theta. So I just need to figure out what sine and cosine are. So we get 2 sine theta, which will be opposite over hypotenuse, root 4 minus x squared divided by 2, and then cosine theta, x over 2. We have a 2 here, and we can cancel this 2. So all we're left with is x square root 4 minus x squared divided by, and we're done. I'm going to give you a harder version of this problem. Instead of using the double angle identity, instead of having 2 times some angle, you're going to have the half angle identity. So try one. Evaluate cosine of tangent inverse of 5 over 12 divided by 2. So notice that you have an angle theta divided by 2. So you need to use the half angle instead of the double angle. Again, assume your angle is in quadrant 1 so you don't need to really worry about figuring out what quadrant half of an angle is when it's in quadrant 1. Any angle in quadrant 1 will be halved into the same quadrant. So if theta is in quadrant 1, theta over 2 is also in quadrant 1. Next topic I want to talk about is the product to sum formulas. Now, the product to sum formulas are not all that important. I usually don't like to have students memorize these, specifically because they're really, really easy to derive if you know your sum and difference formulas. So recall sine of theta plus phi is equal to sine of theta cosine phi plus sine phi cosine theta. Now the subtraction sine theta minus phi is equal to sine theta cosine phi minus sine phi cosine theta. Similarly, we have our cosine. Cosine theta plus phi equal to cosine theta cosine phi minus sine theta sine phi. And cosine theta minus phi is equal to cosine theta cosine phi plus sine theta sine phi. We use these to derive the product to sum formulas. It's very, very easy to show. Sine theta cosine phi is equal to 1/2 sine theta plus phi plus sine theta minus phi. So if we take this formula and we add it to this formula, add them together on the left side, add them together on the right side. This is the positive version of this negative value. So when we add them, these cancel, and we're left with just 2 times this, which is the left-hand side here. Divide by 2, and you're done. You get this formula. Now you can derive all 4 of the product to sum formulas doing this. And this is why I don't think that students should memorize this. It's really easy to just rederive them using these, which you absolutely should memorize. Cosine theta sine phi is equal to 1/2 sine theta plus phi minus sine theta minus phi. Cosine theta cosine phi is equal to 1/2 cosine theta plus phi plus cosine theta minus phi. And lastly, sine theta sine phi is equal to 1/2 cosine theta minus phi minus cosine theta plus phi. As I said before, I don't think that these are super important, so memorizing these is not that big of a problem. They come up when you have very nice numbers. For instance, when we have an example that looks like this. Evaluate sine of 52 degrees, 52.5 degrees, times sine of 97.5 degrees. Well, what do we do? Well, finding these values independently is actually kind of challenging. It would be very, very difficult because you have the 0.5 degrees. So even if we doubled these and said, let's use the half angle, this would be 105 degrees, which is not on the unit circle. So you would have to then use a sum and difference of angles. It's a long process, but it's beside the point anyway. If you use the product to sum formula, then this becomes very easy. This will simply be 1/2 cosine 52.5 degrees minus 97.5 degrees minus cosine 52.5 degrees plus 97.5 degrees. This then becomes 1/2 cosine of negative 45 degrees, which is the same thing as cosine of 45 degrees because cosine is even, minus cosine of 150 degrees. Cosine of 45 is, of course, root 2 over 2, quadrant 1. And cosine of 150 is in quadrant 2, and this will become root 3 divided by 2, but it's negative. So these two, this becomes a positive, and we end with just 1/2 root 2 plus root 3 divided by 2. So when you have really nice numbers like these, the product to sum formulas and sum to product formulas can be very nice. But generally, this is not the case. So again, I don't find these as being very important at all. Next, I'm just going to give you the sum to product formulas, but we're not going to do an example on them. Sum to product. Sine of x plus sine of y is equal to 2 sine x plus y divided by 2 cosine x minus y over 2. These are actually equal to the product to sum formulas with a substitution for theta and phi. Sine x minus sine y is equal to 2 cosine x plus y over 2 sine x minus y over 2. Cosine x plus cosine y is equal to 2 times cosine of x plus y over 2 cosine x minus y over 2. And cosine of x minus cosine of y is equal to negative 2 sine x plus y over 2 sine x minus y over 2. Again, I don't like these that much. I think that these are kind of a waste of time to go over. What I think is more important is getting down to proving identities. I think that's very important in this chapter. Most instructors will test on these all the time. Let's do another example of this just for practice. Prove the identity. Sine of x plus cosine of x, quantity squared, is equal to 1 plus sine 2x. Okay, so remember how we prove identities. We should be practicing this every single section. We start with one side, and we use a chain of identities to get to the other side. So here, I'm going to start with the left-hand side. I think the left-hand side is a little bit uglier, so let's start with that. So we have sine of x plus cosine of x, quantity squared. I think the easiest way to do this is just FOIL it out. It looks like the logical next step, so let's do that. We get sine squared x plus 2 sine x cosine x plus cosine squared x. Now, write that as FOILing out. That was what we did. In the next step, notice that we have a sine squared x plus a cosine squared x. And if you remember, that is an identity. Sine squared plus cosine squared is equal to 1. So now we have 1 plus 2 sine x cosine x. And that is from the identity sine squared x plus cosine squared x is equal to 1. The Pythagorean identity. And last, we have the double angle sine identity. Now, I'm going to have to go way back right here. Sine 2 theta is equal to 2 sine theta cosine theta. Now, a lot of times we go from the left side to the right side, but it's also important to understand that we can go from the right side to the left side. If we have something that looks like this, we can rewrite it like this. And that will help a lot in calculus. So I would recommend you understanding this concept now. So this then becomes 1 plus sine 2x from the identity sine 2x is equal to 2 sine x cosine x. And then you're done. We've reached the right-hand side, so we're finished. Try one. Prove the identity cosine to the 4th x minus sine to the 4th x is equal to cosine 2x. Now this one's a little bit tricky. So I would recommend taking a look at it for a bit, but you should notice that a 4 is a square squared. So cosine to the 4th is the same thing as cosine squared squared. And I think that should help you for the next, for that problem. Last problem. Let's prove the identity. Tangent x over 2 plus cosine x times tangent x over 2 is equal to sine of x. We have a pretty clear front runner on which side is uglier in this one. We start with the left-hand side. So you might be tempted to say, look, we have a tangent x over 2. Let's use the half-angle identity. Not wrong, but it will take you a little bit longer to solve the problem. Take a second and look a little bit closer. Notice that we have a tangent x over 2 here and the same thing in the second term. Let's rewrite this really quickly so I can start the problem. The tangent x over 2 plus cosine of x times tangent x over 2. Now, since we have tangent of x over 2 in both terms, I can factor that out. So we have tangent of x over 2 times 1 plus cosine x. And we just factored out tangent x over 2. You should get used to writing your steps out, mainly for your instructor's sanity, but also to help you learn as you go back and look at the steps that you performed. Now we can use the half-angle identity for tangents. We have tangent of x over 2 can be either one of these. Now, I think we should pick this one because it's the obvious choice. We have a 1 plus cosine x here that's being multiplied. And here, if we choose this one, we have a 1 plus cosine x that will be in the denominator. So they should cancel out. So this will then become sine of x over 1 plus cosine x. And then this carries down, 1 plus cosine x. And of course, the step we performed is tangent of x over 2 is equal to sine of x divided by 1 plus cosine x. And then you can see that we just canceled these. And we're just left with sine of x. And that's it for that problem. All right, that's going to be it for today. I will see you all in the next lecture.